Hi everybody, this is the notes for Exponent Rules. So this is pre-calculus version. We're going to move pretty fast through some of these rules that you've been using for a while. So one thing to remember is you can only use these rules with the same bases, right? So if you have x squared times y squared, you're not allowed to use these rules because one has x and one has y. You can only apply it if it's like x squared times x squared or x to the third. Right, it needs to be the same base. So the first rule is the product rule. When multiplying monomials that have the same base, we add the exponents, right? So in this case, if we're looking at this rule algebraically, we have x to the a times x to the b. We would have x to the a plus b, right? So for example here, if we're just looking at some simple examples, we would add these exponents, h squared times h to the 6th would be h to the 8th power, right? If you really wanted to like spell all these out, you could write like h times h and then 6 more of them, right? And we would have h to the 8th power, right? All these being multiplied together. We go ahead and add each of these. So x to the 9th times x squared times x1 would be x to the 12th power 9 plus 2 plus 1. Same thing can happen here, even when it's in parentheses, right? We're multiplying together the ones that have the same base. So we're saying, okay, negative 2 times 7 would be negative 14. We have a squared times a to the third makes a to the 5th power, and b times b would be b squared, right? So we these are like traditional ones you've been working with for a really long time. Same is true for the quotient rule. When dividing the monomials that have the same base, you're going to subtract the exponents, right? If you have x to the a divided by x to the b, you would have x to the a minus b, and that's going to let us to see how many. I'll show you one that is condensed here. We have x, 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 x. There we go. 9x's over 4x's, right? We know x divided by x is 1, 1, 1, and 1, and we're left with x to the 5th power. So we have 5 x's there. We could have done the same thing by just subtracting the 9 minus the 4 and getting the 5. All right, so that's where those rules are coming from. So written a different way for this one, I'd have x to the 5th minus negative 2 becomes x to the 7th power. We'll talk a little bit about negative exponents here in a moment, but that's how that one works. And then if we have more complicated examples, 36 divided by 9 ends up being 4 on top. If we have m cubed with m1, we're taking like 3 away from 1, we would have m squared here, and then n to the 5th divided by n to the 4th would be just n at the end, right? If it's helpful to you, you can, of course, like write out these 1, 2, 3 over 1 and cross them out, and then 1, 2, 3, 4, 5 and cross out the ones that cancel. That's how we get this one here, and these two make that one there. Right? That's how we do it. You can also just remember the subtraction. For the power rule, right, to raise a power to another power, we multiply the exponents, right? Multiply. So that's when we see something like this, like x to the a power to the b power is like x to the a times b. So we're essentially saying on this number 1, we have 7 of these things. So we'd have like 7 x to the third, x to the third, x to the third, 7 times. And you can see the immediate need for exponents because I don't want to write all those things out all the time. But I am going to have, and then each of these would break into 3. I'm not going to write them all out because there are 21 of them. So x to the 21. We do 3 times the 7 to get the 21. Right? Same is happening here. We have 3 of these things. So we have 2x squared times y, 2x squared times y, 2x squared y. If you write it all out, it's easy to see that we have 2 times 2 times 2 would be 8. X squared, x squared, x squared becomes x to the 6th. Y becomes y to the 3rd. Alternatively, we can see as long as everything's multiplying, we can just pop these right on here. We want to be careful that there's not adding and subtracting, because that's how we get into that trouble. But as long as everything's multiplying, we can do the same thing here. So we would have 3 squared, x to the 8th, z squared, over, and then this also distributes to the bottom here. So 7 squared and y to the 10th, right? Because it was y to the 5th. So I'm just going to simplify here. 9, 8, x to the 8th, z squared, over 49, y to the 10th. All right, so we have some quick examples here for this one here. All right, for our next one, we have our 0 exponent rule. Any base except 0 raised to the 0 power is equal to 1. So x to the 0 power is 1, just like that. So 5 to the 0 power is 1. This whole thing to the 0 power is 1. And then be careful with this one. The 0 only applies to the x, right? So we have x to the 0 power turning into 1 here, but we still are multiplying times -3. So this one would be -3 as our answer there. So just an FYI there as we're looking. And then we have 2 more. Hang tight. So negative exponent rule. If a factor in the numerator or the denominator, so no matter where it is moved across the vinculum, the sign of the exponent is changed. So basically, if we want to turn a negative exponent to a positive exponent, we cross the line, the division line, and we change the sign. So in this case, we see that this is like over 1, right? In order to make this positive, in order to make the exponent positive, we need to move it to the bottom of the fraction. So it becomes 1 over x to the power of a. So we see how that plays out here. If we have a -3, it becomes 1 over x to the 3rd. If we have a -7 in the denominator, this term's going to move up there, so it's going to become a to the 7th. And then again, just like on the 0 on the last example, this is sort of times 7, right? Times 7 like that. So the 7 is going to stay on top, but the x to the power of 3 moves to the bottom. Right, so it's, if we have something like this over this, right, then the y is moving to the top and becoming positive, x is moving to the bottom, becoming positive. Okay. If something was already positive on the top and we have something negative on the bottom, that positive thing stays up there on the top, and then this one would move up there next to it, like that. Right, so we can move them around using positives and negatives. All right. And then the last one, and this might be like the one that we haven't seen the most, is a fractional exponent rule. The denominator of a fractional exponent is the index of the radical. So the root goes on the bottom of the fraction. So this right here is going to swing out in front, and it becomes the exponent. I'm sorry, the index, right? Becomes the index, and then x to the power of a stays here. So if we have, let's use an example. If we have something like this, the 2 is going to swing out in front, so we're going to have the square root of 36 to the 1 power. The 1 power we don't need to write, so just square root of 36 would be 6. So a 1/2 power is like a square root. So you might write something like this is like a square root. If we take this cube and move it out in front, we have the cube root of 27. It's like something times something times something. 3 things make 27. That number is 3. If you think about 25, you're taking this and moving it out in front. So you're taking the square root of 25 and then cubing it. So you can do 25 cubed and then take the square root, but I would recommend doing 25, square root of 25 we know is 5, and then cubing it would be 125, 5 times 5 times 5. And then finally, this one moves out front here, so cube root of 8 squared. We would have Cube root of 8, we know 2 times 2 times 2 is 8. So we'd have 2, and then square that becomes 4. If you wanted to do it a different way, you could also see, okay, I know that 8 squared is 64, and the cube root is something times something times something gives me 64. That something is 4. The cube root of 64 is 4. So same answer you can do there. So these are my exponent rules. We use them in unison to each other, right? So whenever we see multiply, adding, dividing, subtracting, etc. Right? So we're going to see some examples here, and we'll be able to use those rules to combine. So for example, on this first one, I see that my bases are the same here. So I know that I'm going to add the exponents. So 5 stays as my base. And then I'm going to add 2x minus 3 plus 5 minus 4x. So I'm adding these two exponents together, which is going to give me, I have 2x plus negative 4x would be negative 2x. And then we have negative 3 plus 5 would give me positive 2. Because there is a negative there, I know that this needs to go to the bottom of a fraction, right? The negative here is going to tell me to do that. However, I want to take the negative out of the whole thing first. So negative, I'm factoring out that negative there, it becomes minus 2, like that. This negative is going to force it to the bottom of a fraction. So I'd have 5, 2x minus 2, and I'm putting that 1 on top. Nothing else is staying there. So that is how that first one is there. A little bit more complicated than what we've seen in the past, but building on the same examples. So here we're using the product rule, right, to add them together. And then here we are using the negative exponent rule. Right? Negative exponent rule. Right? So we have those two there. Let's look at number 2. Number 2, I want to check, do they have the same base? They do. They have all the same base. I want to combine the top first in order to make sure that it's in 1 before I do that subtraction. So I know product rule means that I can add the exponents here. Right? Adding, so I would have 2. I have x plus 3x would be 4x's plus 4 over 2x plus 1. Using so that's my product rule. Using the quotient rule, right? Using the quotient rule, I know that we subtract them. So I have 2, I have 4x plus 4 minus 2x plus 1, right? So I have 4x's minus 2x's would give me 2x. And I have 4 minus 1 would give me positive 3. I don't have any negatives, so I know that this is my final answer. Right? So we use the product rule first to combine them together in this section here. And then we use the quotient rule to subtract them into this format here. Awesome. Let's look at number 3. Number 3, I'm going to use the power rule here. So I'm distributing this in here. So I have 4 to the power of 3x minus 6 times 4 to the 2 minus 2x. They do have the same base, so I am able to use my product rule, right, multiplying together, right, in order to add the exponents. So I have 4, I'm doing 3x minus 6 plus 2 minus 2x. So I have here the original 4 as my base. I have 3x plus negative 2x becomes just x, and negative 6 plus 2 becomes negative 4. This would be my answer for number 3. I don't need to factor out the negative on this one because it's not leading, right? It's not at the beginning. It's not with x. So I'm going to leave it as x minus 4, right? That's different from number 1, right? On number 1, we had the negative in front. The negative in front here. That's why we factored it out. On this one, it's different. It's not leading, so we're going to leave it there. Awesome. Moving and grooving. Number 4. All right. So first thing I notice right away is that the bases here are not the same, right? I see 2 of them have 2's, but 4 is not a 2. One way that I could solve this problem is by turning 4 into 2 squared, right? Turning 4 into 2 squared. That allows me to say, okay, I have 3x plus 1 still outside, and then I'm just going to copy down the rest of the problem, right? Same exact problem. I just changed my 4 into a 2 squared, right? So we can be flexible in that way. That allows me to use my my power rule. So I'd have 2 to the 6x plus 2 times what we had from before. I want to combine these together. So now that I have the same bases, now I can combine them. I'm going to add these using the product rule. So 2, 7x plus 1 over 2, 5x plus 3. And then using the quotient rule, I want to subtract these. So I have 2, 7x minus 5x would be 2x, 1 minus 3 would be negative 2. Be careful of your order there, right? It's 1 minus 3 rather than 3 minus 1. So we have this as our answer here. All right, two more. All right, let's look at this example. So I know that the negative 2/3 applies to everything, right? Applies to 4 things there. So I know that I'm going to have 216 to the power of negative 2/3. I have x to the third to the power of negative 2/3. I have 125 to the power of negative 2/3. And I have y to the 12th to the power of negative 2/3. So you can see that I took the negative 2/3 and I plugged it onto each element of this term. So remember with my negative numbers, right? It's moving, in order to get rid of a negative, I need to move that whole thing to the bottom. In order to get rid of this negative, I need to move it to the top. So what I'm going to do is I'm really just going to like flip them, like 125 to the 2/3, y 12 2/3, 216 2/3, and x to the third 2/3. So everything can become positive because it moves to a different location. And then remember that this guy's moving out front here. So cube root of 125 squared. And same thing happening here. Cube root of 216 squared. That's how I'm going to deal with my numbers. And then here I know that I'm multiplying. So 2/3 of 12 would be 8. Right? If you want to do it this way, you can. You get 24 over 3, which gives you that 8 there. And then 2/3 of 3 would just be x to the 2 power. So 3 over 1 times 2 over 3, 6 over 3 becomes 2, like that. Almost done, almost there. So I know the cube root of 125 is 5, and it's still being squared. And I know that the cube root of 216 is 6, because 6 times 6 times 6 is 216, and that's being squared. So I'm going to have 25 over 36, and still bringing down y to the 8th, and x squared. This is my final answer for that question. So we had a lot of things here. We applied the power rule, right? We applied the power rule to distribute it into each of the different pieces here, right? We applied the negative exponent rule to flip them, right? That's our negative exponent rule. Let's see if I can do this. That's our negative exponent rule happening there. We changed the radical, right? We changed the radical, so we used fraction exponents to turn it into rationals. That's what's happening right here. And we also used power rule right here, right, when we multiplied those in. Right, so lots of things happening here, but super complicated problem can turn into a much less complicated answer. All right. Last one. All right, so I know the index of this is 2. So I know that this, if I was to like multiply it back up there, is actually technically like 1/2. So I have this, x to the 4th. It's actually technically all to the 1/2 power because it's inside of this fractional exponent. So we have the fractional exponent rule happening here. I need the base to be the same. I see 3 and 9. So I'm going to go ahead and change 9 into 3 squared with the x minus 4. Distribute this in with power rule. So 3 to the 2x minus 8 times 3 to the 2x plus 2. Remember, this is still all 1/2. I'm going to go ahead and combine these. Now that they have the same base, I know that we can add the exponents. So I get 3 to the 4x minus 6. It's still half. Now I can use my power rule to distribute in 3 to the 2x minus 3. Right? Half of 6 and half of 4. So I get this one as my answer. Pretty cool. Pretty cool. All right. Okay, team. So you have your assignment here. You're going to follow each of the different properties. You have your answers at the bottom. You have the problems that you're trying each here. You should find the answers. Let me know if you found a mistake, and we'll rock it out. Thanks, team. Bye-bye.